Hello. We are going to continue lesson 3.3. I am sorry for being out today. I will be back on Wednesday. For today, we are going to do a warm-up and then we're going to get into it. We are going to do our warm-up on the, oh my goodness, where is it? On the Add Puzzle, so you do not have to go find it on Amplify. This is a picture of a house. This picture fell apart due to an earthquake. Your first question that I would like you to answer is, if we don't have earthquakes, can we feel our plates move? Yes or no, and why? Please give me what you think. My second question for you is, how much do you think the plates move on a day-to-day basis? So each day, how much do you think they move? And then lastly, how much do you think the plates move per year? So there's 365 days in a year. So how much do you think they move per year? That is the warm-up for today. And now we're going to continue into it. So we're going to look at observing how plates move today. We do have a new unit question, chapter 3 question. Yesterday we did answer our chapter 2 question, which was, how did the South American plate and the African plate move? And we figured out that they moved by diverting or moving away from each other because it was a divergent plate boundary that was between them. So our chapter 3 question is, how did the Mesosaurus fossils on the South American plate and the African plate get so far apart? We're trying to figure out at what rate did they move. So claim number 1 is that the South American plate and the African plate moved apart suddenly, super fast, and just like all of a sudden split apart. Claim number 2 is that South American plate and the African plate moved apart gradually, so super slow, and it took a lot of time for them to move. What I would like you to do is please tell me which claim you think automatically right now, claim 1 or claim 2. Whoa, skipping over things. Okay. Whoa. Okay. We are looking at a new investigation question. This is different than one on the board, but we are going to look at this investigation question for this chapter. So, our investigation question is, what do we know about plate motion that is currently taking place? So what do you know about it right now? 2 questions before, well, I think we have a few other questions as well. But first question is, how fast do you think the plate below us is moving? You guys know that we are standing on a plate and we are technically moving right now. So how fast do you think it is moving? And also, what direction do you think it's moving? Do you think it is moving north? Do you think it's moving east? Do you think it's moving south? Or do you think it's moving west? If you don't know, give it a guess. It's all a prediction. And that is a-okay with me. Next, I have a video that we're going to watch about geologists and how they use GPS, which is something that many of you probably have used in your daily lives or know-ish what it is. So I want to know, what do you know about GPS? Do you know what it stands for? Where have you heard it? Where have you used it? Give me all of your knowledge about GPS and what it is used for that you know of. Oh, this video does not play on here, so I will play it on another thing. This video is about GPS and how scientists use it. Give it a look.
Geologists use GPS, or Global Positioning System, to track the motion of Earth's plates. You might be familiar with GPS because smartphones and many cars have built-in GPS receivers. They can work with mapping applications to show you where you are at any time, so you might never be lost again. GPS requires 2 parts, a receiver on Earth and satellites in space that send radio signals to the receiver. Once your receiver gets signals from at least 3 different satellites, it can accurately calculate your position on Earth. And if your receiver moves, the GPS system can measure the exact speed and distance you've traveled. This kind of accuracy makes GPS really useful for geologists who study plate motion. Plates only move a few centimeters per year, which is very hard to see, but using GPS, they can easily measure how much the plates are moving. Geologists can install permanent GPS stations into rock on the Earth's surface to track how much the plates move over time. This GPS station is not in the same spot it was a year ago, but we can only tell because the GPS receiver was able to measure the tiny amount of movement that happened. Plates move such a small distance each year that it's not really visible to our eyes. But as the GPS receivers continue to move, geologists can measure these very tiny movements over time. The readings can measure exactly how fast the plates are moving and in what direction. So even though we can't observe plates moving with our eyes, geologists can study them using accurate and reliable GPS data.
Okay. So that's the video. Sorry guys if you can hear my heat turning on. But some really good information about how GPSs are used in order to track the plate motion. With that, here is a plate motion map. So this is showing us the movement that each plate takes. And it does have a key down here that tells us quite a bit. Right here is our plate. You cannot see Michigan because it doesn't have the lakes on it, but we're about right here. So we are on the North American plate. You can see that there's different ways that our plates move. So right here we have a plate boundary, and this plate boundary is a convergent plate boundary because those arrows are coming towards each other. Over on the west coast we have a transform boundary, meaning that they're sliding past each other. Down here at the south end we have another convergent boundary, and then I want you to guess / use the key to figure out what boundary is on the east edge of our plate. So look at these arrows on the east edge and tell me, is it diverging, converging, or transforming? Go ahead and choose one. You'll also see there's numbers on this map. These numbers represent which rate the plates are moving per year. So these are centimeters per year, and you'll see that they range. We have like 1.7 down here and all the way up to 17.2 centimeters, which is a lot comparative, right? Centimeters are definitely smaller though than some may think. I know we talked about your knuckle and the middle part of your finger being an inch. So if you look at the middle part of your finger, that's about 4 to 5 centimeters. So think about that, okay, and think about how many knuckles or middle parts of your finger would you need in order to come up with 17.2 centimeters per year, or 1.3, right? That's way less than you would think. Whoa, I don't know what's going on. It's making it switch fast. We do have a vocabulary word. That vocabulary word is rate. A rate is how often or how fast something happens. So where you might be a little bit more familiar with rate is when you are driving a car when you get to 16, or if your parents are driving a car, there is a rate that is measured in miles per hour. So it calculates how far your car is traveling, and it divides it by how many hours you're driving, and that will be the speed at which you're traveling. This happens quite a bit. Another one would be your heart rate. So if you can find your heart rate, that is the beats, and then they divide those beats per minute, and in order to get your heart rate. So if they normally calculate it over, I believe, 2 minutes. So you would start your heart rate, and you'd start counting however many beats you can feel, and then you would divide it per however long you measured it for. So let's think about the GPS data and how it helps us answer the investigation question. So from the video in the plate movement map, at what rate are plates moving right now? Thanks to what we know from GPS data. So are they moving super duper fast? Or are they moving super duper slow? Which one do you think? GPS data tells us that Earth's plates move at only an average rate of only a few centimeters per year. So we don't know. What we don't know is if plates move at this rate over long periods of time, because we haven't had this amount of technology for that long. We've only had it for a good few, probably a good 50 years or so, maybe a little bit longer than that, but not by much. So they are able to start collecting the data, but they're not able to figure out over, hundreds of years or thousands of years, because we haven't been able to collect that data. The simulation that we've looked at quite a few times helps us observe a model of plate motion that happens over the millions of years. Remember, models are a good way of helping us understand what happens over a longer period of time than what we can see with our eyes right now. So today we're going to use the simulation to measure how far apart two plates move over long periods of time. We're going to look at that timepiece, and we're going to use a GPS tracker that is in the simulation. So now we're going to look at how to measure distances in the simulation. I am going to do this all on my simulation on my computer. And we're going to talk about how to calculate the rates. So here I have our simulation. I have added 2 continents, and then we're also going to drag one of these markers on. So these markers are just a good way of tracking how far, oops, oh gosh, I didn't mean to erase that. They track how far the plates move over the time period when we click run. So what I'm going to do is I'm just going to put one down, and I'm going to set a boundary. We'll do divergent because that's what we've been talking about with our mid-ocean ridge in the middle of South America and Africa. And then I'm going to click run. Mind you, I am going to stop this let's stop it at 50 million years. I'm a little bit over, that's okay. So I have my simulation, my model that is in front of me. You'll notice that my GPS tracker did move, and we're gonna figure out what the rate is. So if I click on this, it gives me a distance. It gives me 589 kilometers, which is km. And then I also have a time. So what I can do is calculate a rate. How to do that is I take the distance, okay, 589. I'm going to do it on my computer. Calculator. Okay. I'm going to take my distance, 589, and I'm going to divide it by the amount of time that the simulation ran. This was 52 million years, mind you. So this is 11.3-ish. We're going to round 11.3 kilometers for 1 million years. So it's not for just a singular year. This is not a rate for a singular year. It is a rate, though, for 1 million years. This is a very small distance. This is a good way that we can figure out how long it takes for us to travel, or how long it takes for the plates to travel in general. I mean, we can really use that model that we have, especially on the simulation. So we're going to skip over using the table that it provides us on Amplify, but I am going to reset the simulation, and I'm going to clear everything, I'm going to reset it. And then I do want you to do the math like I just did and tell me the answer that you get. So I'm going to click run and we're going to pause it at, let's do 100 million years. Oh, it's going to be off the, oh no, I hope I can find it. Oh no, hold on, that might not work. Let's try again. We'll place the marker closer to the plate boundary. That way we can see it in 100 million years. Okay, let's try this. Oops, we have a little bit of a, that's fine. Okay, 100 million years. Let's see if I can get this on actually 100 million years instead of off of it. 60, 70, 80, 90, and stop. Ooh, 99. Oh, 100K. So 100 million years is the time. So I'm going to click on this. Your distance is 1,130 kilometers. I need you to go to Google. I need you to look up calculator. You have to put 1,130 first, okay, because that's the distance. And then I want you to divide that by 100 million years to figure out how many kilometers does it move per 1 million year if it's now over 1,000 million years. Okay, now that we have calculated some of the rates, I want you to start thinking of the rates in the context of your own life. So we need to start thinking about something that is 12.4 miles away from our school and how long it would take to walk there, and how long would it take then also for the plates to move that far apart. So here's our school. Okay, that red dot, 12.4 miles away would be about Mason. Okay, that's where that blue line is right down here. So I took Mason, okay, and I wanted to see how long would it take us to walk from our school to Mason. And it takes almost 5 hours to walk all the way over there, which is pretty crazy. So, think about that. Think about how long it takes us to just walk 12.4 miles. Now think about how long it takes those big, massive pieces of hard solid rock to move 12.4 miles away. It's going to definitely take a really long time. It takes them slower than it would ever take us to walk there. Probably millions of years in order to move that far. So the simulation allows us to see how plates move great distances over millions of years. We would not be able to observe this movement in our lifetimes. These are things that happen within millions of years, and we can see how long it takes, just in these last 50 years. But once we're able to collect that data over a long period of time, then we're really able to get a sense of how hard it is for these plates to move, or how long it takes these plates to move. Reminder that this is our plate movement map. I would like you to answer a few questions, so please make sure that you're paying attention. Right here, okay, I want you to answer the question of what is the 1.7 and what does the 1.7 represent? Please use the key because it will tell you exactly your answer. Okay, what does the 1.7 mean? I want you to please type that in. And then also looking over by South America, by this 3.3, this plate boundary, what type of plate boundary is that? Is that divergent, convergent, and transforming? What do you think? Go ahead and enter that now. And we're on to our key concept. Our key concept is Earth's plates travel at a rate too slow to be experienced by humans. This takes way too long. We will never be able to experience it all in our lifetime. We will be able to get and collect some good data, but definitely not all the data that we need. Okay, make sure that you have done this and finish it all the way to the end and click submit. And then there is a booklet on Google Classroom that you are now moving on to. please make sure that you take your time and you read all of the booklet questions. You do need to do the booklet. It is required. So have a good day. Email me if there's anything crazy or important that you need to tell someone. But also please be kind to each other and to Miss Miki.